Okay, so we have seen how the definite integral can be used to construct distances. We have seen how the definite integral can be used to construct areas. The next couple sections are going to be about using the definite integral to construct the volumes of certain solids. Not any solid, although the definite integral could be used to construct volumes of really any solid you can come up with, but for certain well-behaved solids that are more amenable to analysis. Now, our strategy in the previous section for constructing the area of an irregular shape was to slice it into a bunch of approximately rectangular pieces. Because if the slice is thin enough, then you can assume that the intersection of the slice with the function is approximately constant. And consequently, that slice is approximately a rectangle, and so we can find its area. The definite integral then gives us the machinery to add up all of those little areas, the areas of the little slices, thereby giving us the area of the whole thing. In fact, this is maybe a technical point, but we could actually use this technique to define the area of an irregular shape. I mean, really, that's a technical point, but strictly speaking, we really only know the areas of rectangles and circles. They are defined by their formulas. So we could use this whole method to define the areas of these other irregular shapes. And it would be a good definition because it's consistent with our earlier notion of area, right? Like, if the region bounded by two curves ended up just being a rectangle, then our method of taking integrals would give us back the area that we would expect from ordinary geometry. So in a sense, what we've done is we have extended the classical definition of area to be more amenable to irregular shapes. But that's just a technical point. Now, what we want to do is we want to follow a similar strategy to construct volume, or, if you wish, define the volume of certain well-behaved three-dimensional solids. And the strategy that I'm referring to is the one whereby we slice it into a bunch of really thin pieces and then add up the volumes of those pieces. And when I say add up, of course I mean integrate, because we're adding up infinitely many little slices. And the definite integral gives us the machinery for performing that sort of infinite sum. So, in particular, suppose that we have some sort of region in three-dimensional space, but it's finite, it's bounded. Let us place on the left and right of this region two planes which go through the x-axis at x equals a and x equal b and are perpendicular to the x-axis. So basically, we're taking the vertical line x equals a and x equals b and just extending it into the third dimension so that it becomes a plane. And we assume that our region is in between those two planes. If we slice this three-dimensional region with a plane passing through x, so we are slicing it with a plane which is perpendicular to the x-axis, so we're taking a vertical slice, we're going to obtain a two-dimensional cross-section. So you can imagine, for instance, slicing a loaf of bread. And what do you get? You get an approximately two-dimensional slice, provided the thickness is small enough. Now, the actual cross-section that you get depends on the value of x where you slice it. So consequently, the area of that cross-section is going to be a function of x. It depends on where you've sliced the solid. So let's say that the area of the cross-section is a of x, and let's let dx be the thickness of the slice, which we are assuming to be very, very small. So we're going to use the infinitesimal notation to denote an arbitrarily small but still non-zero thickness. Well, if dx is small enough, then our assumption that that functions are approximately constant kicks in, and so the slice is a cylinder. So remember what a cylinder is. A cylinder is literally just any two-dimensional region that has been extended linearly. So what's the volume of a cylinder? Well, it's the area of the base times the length that it gets extended. In our case, then, the volume of a little slice, which I'm denoting with a d because it's an infinitesimal slice of the volume, is equal to the area of the cross-section times its thickness, right? So a of x, that's area of the base, dx, that's its length. So, to obtain the full volume of the three-dimensional solid, all we need to do is add up all of these little volumes. And by add up, of course, I mean integrate, whereby we obtain this formula, integral of a of x dx. Over some interval, right? These are the a values that bound the solid. Now, this definition isn't very practical if we don't have a formula for a of x, right? As it is, this is still a somewhat abstract statement. So, in order for us to actually do any computations with this, we are going to have to choose three-dimensional solids such that when you take a two-dimensional cross-section of them, you get an ordinary shape. Whose area you can easily compute. In particular, we are going to be looking at three-dimensional solids that are called solids of revolution. Solids of revolution are the shapes that you get when you take a region in the plane and then rotate it about some line, called an axis of revolution. So actually, I should mention that. Or I'm sorry, the axis of rotation. And if you can't visualize what the heck I mean by that, don't worry, because we're going to do a bunch of examples. The point being that if we are focusing on solids of revolution only, then if we take a cross-section of a solid of revolution along an appropriate axis, we will end up getting an annulus. And recall, an annulus is just a circle with a smaller concentric circle bitten out of it, also called a washer. And the reason this is convenient for us is because we know what the area of an annulus is. I mean, it's literally just a circle with a smaller circle cut out of it. So, if the radius of the big circle is big R, and the radius of the interior circle is little r, then the area of the annulus is just pi big R squared minus pi little r squared. And I just factored out the pi here. So it's literally just the area of the big circle minus the area of the little circle. So that's why we're focusing on solids of revolution, because in this case at least, we have an easy formula for the area of the cross-sections. Consequently, oh yeah, and by the way, an annulus where the inner radius is 0 is just a circle. So circles are also annuli. So I'm not missing anything by saying that the cross-sections are all annuli, because I mean, some of them are going to just straight up be circles, but that's fine. Those are just annuli where little r is equal to 0. So, given that we will cut the solid in such a way that the cross-sections are annuli, we would then obtain this formula. So, literally all I'm doing here is I'm taking the formula for the annulus and putting it in here. Pi is a constant, so you can pull that out. And then the radii are going to depend on where in the solid you cut it. So that means that they're going to be functions of x, because x in this formulation represents the place in the solid that you slice it. And of course, so this is based on the assumption that we are taking slices perpendicular to the x-axis. Where do I say that? I should say that somewhere. Yeah, we're taking slices. if we slice the region with a plane passing through x. Let me mention that again somewhere, because that really is important. So if our slices are vertical, that is, they are perpendicular to the x-axis. So you can see in thrilling real time how I have never taken a typing course in my life, because I make numerous mistakes. All the same, I do somehow manage to get these notes written. So if our slices are vertical, that is, they're perpendicular to the x-axis, then the volume of our region is given by this formula. I mean, the significance of the slices being vertical means that the outer and inner radii of the cross-sections are going to be functions of x, because we are slicing on the x-axis. And of course, this discussion works just as well if, instead of taking cross-sections perpendicular to the x-axis, we take we take cross-sections perpendicular to the y-axis. So these are horizontal cross-sections. In that case, because our cross-sections are horizontal and they intersect with the y-axis, then all of our slices are indexed by values of y instead of values of x. Consequently, we get the same formula, but the inner and outer radii are functions of y, right? They depend on where exactly we made those slices. Okay. And then I say a little bit more about the washer method here, but before we do that, let's just jump into an example, because I feel like this is the sort of thing that really makes the most sense once you see it done a few times, because it's an argument that's very heavily inspired. Well, not inspired. It is geometry. It's an argument that is geometric at its core. So if you're not drawing pictures, then there's very little hope that you're going to be able to get it. And the principal challenge is really just to figure out what the functions big R and little r are. Because once you have those, you just plug them into the formula and perform the integration, if possible. Okay, so find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals root x from 0 to 1. Okay, so we have the curve y equals root x. We focus on values of x between 0 and 1. We look at the region underneath the curve, and then we rotate that region about the x-axis. And in so doing, we're going to obtain some sort of three-dimensional shape. So let me switch over to G-Algebra and do this in real time. Okay, so we have y equals f of x, so let me put that in as a function, because in GeoGebra it's nice to have control over what you're naming your objects. So let's just go ahead and call that first guy f. We are only interested in values of x between 0 and 1. So what we can do is we can type in function f because that's what this is called, and then 0, 1. And then what that's going to do is it's going to isolate the portion of the curve which is between x equals 0 and x equals 1. And now let's hide that because we don't need it. Furthermore, let's put a vertical line at x equals 1 because that's going to be the right boundary of our curve. So let me just type x equals 1 like so. So you know what? No, I don't like that. Let me type segment, and then let's see. So this is the point 1, 0. and this is the point 1, 1. There we go. So that makes a line segment connecting those 2 points. So this is the region that we're interested in. And we're going to take this region and rotate it around the x-axis. And I claim that that's going to produce some sort of solid. So what do I mean by that? Well, let's bring up 3D graphics. So you can see that in the 3D graphics view, we have the two-dimensional view reproduced, but now there's the additional z-axis. Just checking to make sure that it's being captured. Okay, good. Now, here's how you make solids of revolution in G-Algebra. First off, let's create a slider. So if you just type in n, G-Algebra will automatically make a slider. And let's make that go from 0 to 2 pi, and give it a step size of 0.01 so that it's somewhat smooth. So this is going to represent the angle of the revolution, because when you turn this thing around, internally, G-Algebra has to know what the angle of the turn is. And if we're doing a full turn, then that's from 0 to 2 pi, right, in radians. Now, we type in surface, and we're going to take the 2 curves that are comprising the region that we're rotating around. So one curve of interest is this dude here, and that is being called G. So we take G, we are going to rotate it through n radians, and we're going to rotate it around the x-axis. So x-axis. And make sure you capitalize the A, like so. And let's do the same thing for this line segment. So G-Algebra is calling that line segment H. So surface. So rotate H through n radians about the x-axis. Now watch what happens when I increment the angle. Right now it's at 0, so it hasn't rotated it at all. But as I increment the angle, you will see that it starts rotating the region. And when you've done a full revolution, we now have a 3-dimensional solid. So this is a solid of revolution. You take this 2-dimensional region, you rotate it about some axis, and the set of points that are touched by the region in that rotation becomes the set of points inside your solid. Okay, so this is the solid whose volume we want to find. Now, our strategy is going to be to slice this, and then add up the volumes of all those little slices. So in this case, I think if we slice perpendicular to the x-axis, we should end up getting cross-sections that are circles. And remember, we want to slice this in such a way that the cross-sections end up being annuli. So if we slice it with regard to the x-axis, we'll get cross-sections that are circles, so that's good. If we slice it horizontally, then we'll get cross-sections that, well, they're not going to be circles, at least. They're going to be some region. It'll be like parabolic. In any case, we're not interested in that. We want the cross-sections to be annuli. So, let me show you how we can visualize this. So moving back to the 2-dimensional bit, we are going to slice this along the x-axis. So, let me make another slider. If you type S, G-Algebra will automatically turn that into a slider. And I want this to represent the values of x that we are interested in. So this goes from 0 to 1. Okay? So this represents the place, the value of x where we are going to take the slice. Now let us construct a segment extending from the bottom of the slice to the top of the slice. So from s, 0 up to s, What is this called? It's called G. So S comma G of S. Okay, so there we have our slices. Now, we can get the cross-section by rotating this slice around the x-axis, just like we rotated the entire region around the x-axis. If we rotate just this one slice, then we will obtain the annulus that I've been talking about. So surface. So this slice is being called N, whoops, and rotate that around the x-axis. Now you can see that if, whoops, hang on, let me turn off these other surfaces. So if you rotate that slice, you see that you end up getting an annulus. In this case, it is an annulus where the inner radius is 0, so it's just a circle. And if we move the position of the slice, you can see that what we are essentially doing is we are adding up the volumes of all of these tiny annuli. Because we are assuming that this thing has some thickness. That thickness is dx. So the volume is the area of the circle times the thickness, dx, and then we add that up over all of the possible x values. So, just so you can see, this does indeed give us all of the possible cross-sections. So we are constructing the volume by little pieces. Now, what do we actually need for the formula? Well, we need the radius, we need the inner and outer radius, or radii of this annulus. Well, the inner radius is clearly 0. The outer radius, on the other hand, is going to be this distance. So, what is that distance? Oh, well, it's literally the distance from the x-axis to the function. So, the outer radius is the function value. It is the distance from x-axis to the function, so that's square root of x, by definition. So there we go. So that's how we get that the outer radius is square root of x and the inner radius is 0. Now it just remains to plug in the formula for the volume and compute it. So the formula for the volume is pi integral from 0 to 1. So 0 to 1, that's the range of our x values. Big R squared minus little r squared, which in this case is 0, dx. So this is just going to be the power rule, looks like. So square root x squared becomes just x. Okay, yeah, so that's easy. Don't forget that pi. That pi is always going to be hanging out. Let's see. So antiderivative of x is x squared over 2. Evaluate that between 0 and 1. Oops. Sorry. I'm trying to figure out how to make this look as good as possible, like while I'm actually typing it. So if you plug in 1, we get just pi times 1/2. So pi over 2. If you plug in 0, you just get 0. So there's nothing more to be done. So the volume of this region is pi over 2. Pretty neat. I mean, it really is remarkable. So try to put this in historical context, right? Like thousands of years ago, in the time of the ancient Greeks, they figured out how to take the volumes of squares. They figured out how to take the volumes of circles, or spheres, which is incredible, by the way. If you look up like the ancient argument for how they found the volume of a sphere, it's really ingenious. But things like this really would have been beyond them. As brilliant as the ancient Greek geometers were, and they were truly brilliant, finding the volume of a shape like this really would have been beyond them. And it's just amazing to me and magical just how easily we can do it. Just through the tools of anti-differentiation. So yeah, that even if you think the actual material is boring, which is fair because a lot of it just ends up being tedious computations, try to keep alive in your heart the magic of what we're doing here, and really how truly incredible a human achievement it is. Okay, so let's do a few more examples. Find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0. So x equals 0, that's just the y-axis, about the x-axis. So you take this region, rotate it about the y-axis, and we obtain, again, some sort of solid of revolution. So let's go back to G-Algebra and see what that would look like. So what do we have? We have x cubed. I mean, I'm talking about the magic of doing the mathematics, not even mentioning the magic of this program that I'm using to show it to you in the first place. Anyway, yeah. What else do we have? We have y equals 8, which is the vertical line up here, and we have x equals 0, which is the y-axis. So the region that we are interested in is this region here. This region. We're going to rotate this around the y-axis and obtain a solid of revolution. Also, let me isolate the bit of the curve that I'm actually interested in. So let me get rid of this and just put a line segment instead. So that would connect 0, 8 to 2, 8. There. So now that's just a line segment. And if we isolate the bit of the function that we're interested in, that goes from 0 to 2, looks like. Okay. So turn that off. Yeah, there we go. So that's the region that we want. Now let's bring up the 3D graphics and rotate it. And you know what? We really don't need to have the y-axis highlighted there. Okay, so start up our slider for the angle. Goes from 0 to 2 pi. The step size of 0.01 doesn't really matter. I just want it to be small enough so that the animation is somewhat smooth. Now we rotate the curve about the y-axis. Again, the A has to be capitalized there for G-Algebra to recognize it as the geometric object, the y-axis. Similarly, the line segment is called G. There we go. And voila. There is the shape that we are interested in. Sort of a bullet shape. Well, a bad bullet shape. Now, we want to take cross-sections of this, and we want those cross-sections to look like annuli. So, if we slice it along the x, if we slice it vertically, well, that's clearly not going to work. If we take vertical slices, then we would end up getting like parabolas. However, if we slice this horizontally, then I think it's pretty clear that we will end up getting annuli. Really just circles. So we're going to have to slice this guy horizontally instead of vertically.